Okay, so now we're going to move on to something a little bit different, something called Veblen functions. Now, Veblen functions are denoted with the Greek symbol phi, and they have a number in the subscript and input to the function. Now, we ran into a problem where each time we came up with like an infinite nesting of these ordinals and we denoted new ordinals, eventually we're going to come across a problem where we're having to denote new Greek letters, and because there's not an infinite number of Greek letters in the alphabet, we need a better system. So Veblen came up with a system where instead of coming up with new letters, he just came up with an enumeration of the function in the subscript. So this is kind of a way out of that. So starting at the beginning, the first index of the Veblen functions, phi sub 0 of a, is just equal to omega exponentiation, basically. So omega to the a. The next one, phi sub 1 of a, is all the epsilons. Phi sub 2 of a is the zetas, and so on and so forth. So continuing on in this fashion, you can imagine the next step in this would be an infinite nesting of etas, and this would be equivalent to phi sub 4, and things like eta 1. So the next fixed point after that would be phi sub 4 of 1, eta 2 would be phi sub 4 of 2, and so on and so forth. And it continues on in this fashion. So basically, the rules for this are basically to do the exact same things we've been doing before, but just in a different format, basically. So I'll go through the rules vaguely, but they'll become a lot more clear once we start doing some examples. So first off, phi sub 0 of 0 is defined as 1. As we move on to having other numbers in the subscript, so alpha in this case is a successor, which means it's not a limit ordinal, it's a number, so like 3 or something like that. So phi sub alpha of 0, if we diagonalize that to n, we end up making n copies of the previous function or whatever, so phi alpha minus 1 of 0. Now if we have a number in the subscript and we have a number, a non-zero number in the input, we basically do the same thing here. So we make n copies of the previous function, but then we keep this function here, we minus 1 from the inside and put it on the outside. So that might seem a little strange, a little arbitrary, a little like weird why we're doing that, but I'll do an example and I'll show you how it corresponds to something that we've already been doing. I'm going to leave this for now because this is a special case with a limit ordinal in the subscript, so we'll deal with this later. For now, we're going to be dealing with these functions right here. So if you remember, diagonalizing something like epsilon 1 to 3, we get the third element of the fundamental sequence, which is omega to the omega to the omega to the epsilon naught plus 1. So if we do the corresponding Veblen function, we should end up with the same answer. So let's do that. We know that phi sub 1 of a is the epsilons. So to get epsilon 1, we need phi sub 1 of 1. So let's write that down. Phi sub 1 of 1. And we'll diagonalize it to 3. So now we'll use our rules. We need an alpha here because alpha is a successor, which is what we're dealing with. And we have a number a in the input here. So we need to use this function here. So first thing we're going to do is we're going to do n copies of the previous function here. So we're going to do n in this case is 3. So we're going to do 3 copies of alpha minus 1. Alpha is 1 in this case, so we're going to do 3 copies of the phi 0th function. And on the inside, we're going to have phi sub alpha. So alpha is 1, so we're going to have phi sub 1 of a minus 1. A in this case is 1. 1 minus 1 is 0. And then we tack this 1 on the outside here. So what we'll do is we'll expand this out. So we'll turn this into phi 0 of phi 0 of phi 0. So if you want to think of it kind of, it's similar to the fast-growing hierarchy in that there's a subscript and input to the function, and writing it in this way is like nesting the functions type of thing. So if that helps. Phi sub 1 of 0. Oops, I've got the 1 there. Jeez. Okay. There. Okay, so what is this doing here? We know phi sub 1 of 0 is part of the epsilons here. So this is equivalent to epsilon naught. So let's just write epsilon naught over here. Epsilon naught plus 1 would be the inside of this function. Now what's phi sub 0? Phi sub 0 does the omega to the a function. So if we think of a now as our epsilon naught plus 1, this is taking omega to the power of this. And also we could think of the next one down the line here, taking omega to the power of that, omega to the power of that. So really another way of writing this is omega to the omega to the omega to the epsilon naught plus 1, which is exactly what we got here. So perfect. So now these rules seem to be a little bit more clear. You can see why we're doing things like minusing numbers here and adding them on the outside, basically. It's another way of escaping the fixed point trap. So basically you're taking the nth element of this here. So you're creating 3 copies of the omega right here. Then you're minusing the 1 here. So we start with epsilon 1. Minus 1 is epsilon naught. And then we add the 1 on the outside to escape the fixed point trap. So basically Veblen functions have built within them a way to escape the fixed point trap, which is this plus 1 on the inside here. So by following these rules, basically, we have a different way of deconstructing these ordinals. And this becomes very, very important for 2 reasons. One is the one I explained before, is that we don't have an infinite number of these Greek letters. And also, when you start deconstructing these things, like further down the line, they become extremely, extremely difficult. You start having things like a bunch of exponents all over the place, and it's really hard to keep track of where you are. So it's much neater to have some kind of a nested functions to deal with these things. So now let's go further with this, basically. So let's we could translate this into something that we already know, like this, but we can also stay in Veblen notation and go a little bit further deconstructing to see what happens. So the next step here, we have to kind of look at this in a different way. Phi sub 0 of this, what is that doing? Well, like we said, it's omega to the power of this. So what we're going to do is we're going to exploit the idea that omega to the a plus 1 is equal to omega to the a times omega. So now this is going to become phi sub 0 of phi sub 0 of phi sub 0 of phi sub 1. And now we're going to close this bracket here and go times omega. So basically we're doing the exact same thing. We're doing this is equivalent to this here. Oops, sorry, this thing's sketching out a little bit. Come on. There we go. This here is equivalent to this. And then this here is equivalent to this. And we're doing this basically so that we can continue diagonalizing this or whatever. So let's say we have this here. We can then attack this omega here with the 3. And then turn this into phi sub 0 of phi sub 0 of phi sub 0 of phi 1, 0 times 3. And there's a couple extra brackets here. Now to continue on further, what we have to do is we'll break this apart now. We're going to break this apart into 2 copies of the phi 1 function, and then we'll leave 1 out. We'll add 1 to the end so that we can deconstruct that further. So we end up with phi sub 0 of phi sub 0. Sorry. Of phi sub 1 times 2. And then we're going to add the last one on here. So phi sub 0, phi 1. And that's diagonalized to 3. And I'm going to pause this video, actually, and we'll continue on in the next one because this thing is sketching out. So I just have to close Photoshop, and then we'll continue on. Come on.